Okay, off we go. Here's where we were last time. So we were talking about how to deal with the problem of what if your domain is not a rectangle, right? So we defined double integrals on rectangles. We defined iterated integrals on rectangles, and we talked about various relationships. Okay, so if it's not a rectangle, from the double integral point of view, it turns out actually everything's fine. There's a lot of formalities that have to be dealt with. This is not the course to present all those details. So what I want to say about double integrals is they're exactly what you think. It works fine for non-rectangular domains. Basically, your domain, you're going to chop it up into little pieces, and you're going to deal with each piece separately and then add them up. That's exactly what you would imagine it should be. Okay, and we talked through last time about how, what is the corresponding iterated integral, and pretty much everything works fine. The only little asterisk is you have to recognize that because of the shape, your inside bounds are functions of the outside variable. Right, and that's just, again, you can see that from the geometry of the shape. So the very last observation that we made last time is that this three-dimensional picture that we've drawn, it's, again, a nice visual aid in some sense, in some context, to be able to see a dimension represent the value of the integrand. Well, the domain is completely independent of the integrand. So the three-dimensional aspect of this drawing doesn't matter to the question of finding what these inside bounds are. So don't draw an unnecessarily complicated picture. It's just making your life harder, right? Draw only what you need, and all you need is the domain itself, right? So we talked through sort of what the final punchline is going to be. If you want to find an inside bound, let's say if you want to find this a of y right here, well, that's going to correspond to a certain point. We're literally going to see how, whatever value you have of the outside variable as you sort of move in the direction of the inside variable, there is a point, such as this one, that represents where you start in that process. That point is on a certain curve. That curve has some equation. And then in recognition of what it is that you're actually solving for, so, here we're trying to find a value of x, because this lower bound is an x coordinate, then solve for that corresponding variable. Okay, all right, and that's where we ran out of time. So let's actually do one. This is a nice, easy starter example. They won't all be as algebraically convenient as what I'm showing you here, but I think it's always nice to start with a nice little easy one, right, where there's no other, huge distractions of algebra or whatever. Okay, so we've got a double integral to compute. Notice, I didn't start with an application question. I didn't say let's compute the mass of whatever, or let's compute the volume of whatever, right? I just, for whatever reason, we've already got a double integral. Let's just talk about how to convert that to an iterated integral. All right. No particular reason. I'm going to do my slicing in this order. We'll do it in the other order next. Right, but just to get the ball rolling, let's choose this order. Let's see here. So what's the range of values for x? All right, well, x slices look like this. Here's sort of a few x slices. And the first slice is going to be there, which I'm going to say is pretty clearly 0. After all, it's the origin, right? You just need to know what is the x coordinate of the origin. Well, okay, well, that's clearly 0. Right? Sometimes you get lucky. Now let's look at the last slice. The last slice, well, this is that last slice. And again, it's kind of a freebie. It just says right there, x is equal to 1 at that point, so this upper bound is 1. So sometimes they're just staring right at you, and at that point you can just write that down. It's no problem. Okay. All right, now where it gets interesting, though, is how do we find, let's start with this upper bound for the inside y integral. So what is going on there? How does that end up being x? Well, you got to keep in mind, for a given value of x, right? So given an x, So we're going to be moving, for this given value of x, we're going to be moving up in the y direction. And we want to know the value of y. What's that y bound? Well, that comes from this point. I mean, that is the point that you're at when you finish that x slice. Right, so that is that ending point. That point is on that curve. By the way, thank you, picture. We need the picture for that. Right? It's a nightmare to try to figure this stuff out from a purely algebraic manner, and I'm not even going to present such a technique because I do not think that's a good way to go. Right? You really, really need to have a picture. So I can just see from the picture that this point that tells me where I end, well, it's on that line. Which, of course, by the way, we were given this point and that point, which are there and there. So a little bit of, very little bit of algebra you've got to do to find the equation of that line, and you'll find that it has that equation. Okay, so reminder, looking at the inside bound, starting with the upper bound, no particular reason. The bound is determined by that point. That point is on this curve. That curve has this equation. Notice we're going through our usual process here. And so now we just have to solve for what we're interested in. And you do have to be careful about this. You got to make sure to solve for the right thing in terms of the right thing. Let's remind ourselves we are interested in a y-coordinate here. Right? This is a y-coordinate. It's a bound for the dy integral. So in this equation, I need to solve for y as a function of x. And there it is. This is how y is a function of x in that formula. And so that formula, x, is that upper bound. Everybody see that process? By the way, notice it's a function of what it's supposed to be, right? So it's supposed to be a function of x, and sure enough, it is. All right, now let's do the other one. The lower bound, go a little bit more quickly. This time, let's see, to find this lower bound, well, oh, and a reminder, we've selected a value of x. We're moving like so along in the y direction for that value of x. So that lower bound for y comes from that point. That point is on that curve. That curve has that equation. Again, sometimes it's easy. You could just, it's right. It's clearly the x-axis, right? So no problem. Y equals 0. And again, keeping in mind that we are looking for a y-coordinate. This is, after all, a y-bound, so it's a y-coordinate. So we're going to solve for y in that equation, and we get 0. Is everybody on board? All right, now in this example, I did the slicing in this order for no particular reason, just to get the ball rolling. So, okay, boy, what if we go the other way? If we go the other way, it's very analogous, a little bit different. Things work out a little bit differently. Again, you always got to follow the process. Again, this is the process, right? Make sure to always connect the dots in that way. And here we go. Let's see, slicing dx dy. That means that our y slicing is first. That means our slices look like this as I go in the y direction. Yep. Okay, well, let's see here. The first slice is going to be like so. That's pretty obvious. Y equals 0. The last slice is up here. That's literally a given point. That point was given to us in the statement of the question. That's 1, 1, for which the y-coordinate is, again, obviously 1. So again, you get lucky very often, and when it's just perfectly obvious, right there staring at you in your picture, just go ahead and write it down. That's totally fine. Okay. All right, but now let's talk about the inside bounds. So we're going to fix a value of y. I'm going to fix a y. Here then is that y slice. We're going to be moving in the x direction there for our inside bounds. Let's think about the lower bound. Lower bound comes from that point, which is on that curve, which has that equation, following our usual process. Now, slow down. Wait a second. What are we doing? In this case, now this is an x coordinate because I'm trying to figure out what happens as I move in the x direction. So I need to write from this equation, I need to solve for x as a function of y. That feels weird in a lot of cases. A lot of students feel like, oh, aren't you always supposed to solve for y as a function of x? Nope, certainly not here. Right? We need to know how the coordinate that I'm interested in is a function of the outside variable, in this case y, and so our lower bound is y. What do you think? Everybody okay with that? Okay. All right, and then let's look at the upper bound. Oh, well, anyway, okay, fine. So the upper bound, so again, y is fixed, and we're doing like this. Okay, so the upper bound is that, which comes from that point, which is on that curve, which has that equation. And again, sometimes the fish just jump right in the boat, right? This one's clearly x equals 1, so we'll just go ahead and write that down right there. Is everybody happy? Okay. All right. So which way should you slice? You got two options, and suit yourself pretty much. Now, the thing is, in this particular case, you can see it worked out pretty reasonably slicing that way. It was going to work out pretty reasonably slicing the other way. It kind of didn't really matter in this case. Sometimes it does. Sometimes it really matters. Sometimes one order of slicing is much more desirable than the other order of slicing. And so the next thing I'm going to show you here is some examples of where it really matters, where you're going to have a strong preference for one versus the other. Okay, so now I'm not going to go through all of the details of this example. I'm going to hit some particular highlights. I'm going to start with the language that we describe this example with. You see this curve y equals x squared. Fine, and you see this curve y equals 4. Cool. Now let's talk about what this means, bounded by. D is a set that is bounded by those two curves. It means two things. On the one hand, it means D is a region whose boundary consists of those two curves. The problem is there's actually several regions in the plane whose boundary consists of those two curves. So for example, this region here, sort of, up and to the right there, that region, well, the boundary consists of the green and the blue curves. Is that what we were talking about? No. Because the second aspect of this language bounded by, the second part of the story is the region has to actually be bounded. And bounded means that you can put it in a box. It means it doesn't run off to infinity in any direction at all. It's just you can put it into a box or a ball or something like that. Okay. So there is only one bounded region in this picture that is in fact bounded by those two curves, and that's that region right there. Is that cool? Everybody happy with that? So heads up about this, by the way. Part of your job in answering questions of this sort is to think sufficiently about the geometry that you, in fact, do identify the correct region from the language. That is part of the problem. Okay, so let's see here. Again, a couple of highlights of the slicing process. No particular reason. We'll start by slicing dy dx, which means, all right, so I need the lower bound for x, the upper bound for x. You'll notice that the lower bound and the upper bound are both described by points that are on both of these curves. So for both of these bounds, you're going to have to solve, wait a second, these bounds are x bounds. You're going to have to solve for x in this pair of equations, right? And tempting, a lot of students are a little fast and loose with square roots because high school lets you get away with that in a lot of cases. You can't do that. We have x squared equals 4. So many students will just say, all right, well then x equals 2. But nope, x can be either 2 or minus 2. And then it's not hard to persuade yourself that the lower bound I'm looking for, I can see it right in the picture, that lower bound is clearly negative. Again, thank you, picture. We need the picture to draw that conclusion. And so we get negative 2 for the lower bound. And then likewise, you can see that the upper bound is clearly positive right there in the picture. And so the upper bound is positive 2. So that's something you have to keep track of. Is everybody okay with all that? Okay. All right, and then the rest of it's pretty typical. I'm going to let you all think through the inner bounds there. Now, though, let's look at the other order of slicing, dx dy. That means our y slicing is on the outside. That means that our slices look kind of like this. And again, you have to think about first and last, and what is the value of y at the first and last slice. And so, okay, well, fine, but the first slice is here. That's obviously the origin. The origin obviously has y coordinate 0, freebie. The last slice is there. It's right on this curve where the equation is y equals 4. So 4, right? Another easy one. Sometimes it's just nice and convenient, and that's always appreciated. Okay, but now let's fix a y. Let's think about moving along that y slice in the x direction. Let's think about the x bounds. And here's where a lot of students mess up. This is a very common mistake. Let's see here. Let me get my colors straight. Okay, so this lower bound comes from that point, which is on that curve, which has that equation. And here's the problem. A lot of students will say, oh, that's x squared. And then we'll put an x squared there for the lower bound. And they didn't follow the procedure. They didn't solve for the right thing, right? So when I say that, you identify the appropriate equation, don't just then take whatever part of that equation, I don't know, seems like it ought to be. No, you got to literally follow the procedure, follow the rules. Our rule is that we recognize here that we are looking for x as a function of y. That lower bound we're looking for is an x coordinate, right, for the x integral. So in this equation, I have to solve for x, because that's the deal. And when you solve for x, again, you got to take a square root. There's always a plus minus. You got to again think it through. I notice that the lower bound I'm looking for is negative, and so solving for x there, I get negative square root of y. What do we think about that? Everybody see how easy it would be to just kind of carelessly write down x squared, and that would be just dramatically wrong. Okay, and everybody's okay with how this is, again, in fact, prescribed by our process. Okay. Okay, likewise for the upper bound, positive instead of negative, of course. Okay, so now why did I show you this example, aside from it's good to see a bunch of examples, I kind of get the hang of how the process works. Well, I wanted to give y'all my first little bit of advice on how to decide which order to slice. Right, should you do dy dx or dx dy? Which do you want to do? And let's think about this bottom integral. Let's think about how would this play out if I actually had to compute this. And so I'm going to have to take an antiderivative of f dx. I don't know what f is, so I don't know how hard that's going to be, but that is what it is. But then here's the thing. When you evaluate, you're going to have to plug in some square roots into whatever that antiderivative is. That means that the result of your inner integral is probably going to have square roots in it. Don't forget as well, that inside integral is the integrand for your outside integral, right? So your outside integral here is going to be a dy integral of ugliness. Yeah? All else being equal, I don't like how this is smelling bad to me, right? I don't think that's a good, I'm not optimistic that this is going to be a good way to work out a question. Okay, on the other hand, you look at this one here, the inside integral. Well, it's going to have an x squared in it, whatever. It's not that bad. Give me my choice between an x squared and a square root. I'm going to take this. I'm going to take the square over the square root pretty much every time. Right? There's occasional counterexamples. So this one looks not that bad, right? My outside integral here will have an integrand that I am less scared of. Okay, so I'm going to say that this is the one that we like and this is the one that we don't like. Now, do you have to write them both out every time to decide, or is there a little shortcut hack that will allow you to make probably the right choice first guess? And I have a little shortcut argument. And that is, let's try to identify what is it that made this bad news happen. The reason that got ugly is because I had to solve for x. Right? Why did I have to solve for x? I had to solve for x because the inside bounds corresponding to the inside variable are what you got to solve for. So I had to solve for x because I put dx on the inside. Well, I could have seen that coming, right? You look at this equation here. It's really easy to just ask yourself, would you rather solve for y or would you rather solve for x? And I think it leaps off the page. And yeah, I'd much rather solve for y in this equation, right? So, all right, well, whichever variable you would like to solve for, I would like to solve for y, put that on the inside. Whichever variable you would prefer not to solve for, right? Don't put that on the inside because it'll give you a bad result. Yes?
What is the
it not really playing a role in this example. It's the whatever integrand is necessary to make this double integral relevant to wherever this came from in the first place. That's not what this example's about. So it's some integrand. Yeah. Is that cool? All right, so always look at the algebra you're given. Don't worry about stuff like that where it's trivial, right? But any equation where it really matters, I'd rather solve for one instead of the other, let that guide how you order your differentials. Okay, now this won't always be the right, but this is a really, really good sort of general advice, 9 times out of 10 kind of a deal. Okay. Another example. That's going to lead to another little bit of strategy. Generally make us avoid work. Another triangle for our domain. You can slice it in either of 2 different directions. I'm going to let y'all do the top one. It's pretty straightforward. No big deal. Make sure you can do that. Okay. Well, let's look at the bottom one, where I've decided it seems that I want to do dy dx, which means x is my outside variable. So I'm going to be doing my x slicing first, and those slices look kind of like that. The upper bounds for my inner integral then, my upper bounds are going to come from this curve. You can just see, for each one of these x slices, that top value of y is on this purple curve. And here's the problem. That purple curve doesn't have a very nice equation. It's kind of 2 curves. There's the curve on the sort of the left side, and then there's a corner there, and then there's sort of the rest of the curve on the right side. Totally different equation. All right. So I can't then do all of x from 0 to 2 all at once, because then my upper bound curve doesn't have an equation I can work with. So I have to actually break this up into chunks. I have to first let x go from 0 to 1. For those values of x, no problem. My upper bound curve is that. Solve for y, and you get that. And then now for the next values of x, as x goes from 1 to 2, my upper bound for y is now this curve that has a totally different equation, right? This is not the same line. Totally different equation. In which, when you solve for y, you will get something totally different. Cool. Everybody see how that happened? Okay, so again, now we've taken a question, we've kind of done it two different ways, and let's decide which one's good, which one's bad. I hope most people would expect, in most cases, that we like the one that has only one integral to work out, as opposed to having to work out two integrals. All else being equal, who wants to do twice as much work? Right? That's undesirable. So, okay, how do we see this coming in advance? How do we, again, do I have to write out both every time? Would it be nice if I could have a guide that always leads me right to the one that I want? And here's the way I like to see it. There's different ways to phrase this. I think of it as that as I'm going in the x direction, this being what my slices look like, notice at some point we slice through a corner. And roughly speaking, the problem here was that the equation for this part of the curve and the equation for that part of my upper bound curve, well, they were different equations because really they were kind of two different curves in the first place. And this corner is where those curves intersected. And typically, when you have an intersection of two curves, you make a corner. So, very often, the giveaway that you're doing something wrong is that in the middle of your slicing process, you slice through a corner. Yes?
For the second method of how you did it, why is there a lower bound a 0 for the higher bound 2 minus x?
Yeah, sure. Okay, so you're talking about this right here?
Yes.
Yeah, okay. So, all right, so we were looking at x between 1 and 2. And so we're going to pick a value of x somewhere in between. There's our x slice. And the lower bound comes from this point, which is on the curve where x equals 0. Sorry, where y equals 0. And so that lower bound is y equals 0. Is that cool?
Thanks.
Yeah. Yep. All right. Okay. Yeah. So again, my take on this, and there's different points of view on this. You might find something you prefer. Try not to slice through a corner in the middle of your slicing process. Now, it's no problem that we're starting at a corner. That when you slice through a corner, you're going to have to stop the integral you were doing and start a whole new integral. But I was starting a whole new integral here anyway, so that's not a problem, right? And again, not a problem that I end at a corner. I was done anyway. That's not a problem. The problem is slicing through a corner in the middle of your process. That's why you get two separate expressions there. Okay, now let's look at the one where this didn't happen. Going back up to here, as y goes from 0 to 1, our slice is looking like this. And notice, nowhere along the way did I slice through a corner. And as such, it worked out nicely. So again, a nice little sort of, not 100% always going to be the best solution, but very often this will guide you in the right direction. Okay, yeah, try not to slice through corners. All right, last little thing I want to address. Previous examples we've seen the integrand is given. The domain for the integral is given. And I just want to point out that sometimes it's not. Sometimes the domain is something you have to figure out as part of the question. And so this is a nice example of that. We've been asked to consider that surface, which of course we know from before, and this surface, which is a plane, and we want to look at the volume in between. And the volume in between is what I have shaded in gray there, which is a little bit easier to kind of see and work with over here like this. And okay, so that's the volume that we want to compute. And okay, I can slice that up. Right, I can view this as being a bunch of little pieces of volume. Bunch of little pieces of volume. There's one of my little French fries, little piece of volume here. And that's a little rectangular, highly elongated little rectangular box. And so height times the area of the base. Right? So the height, let's think about this carefully here. That height is the difference between the z-coordinate there, which, let's see, that's the z-coordinate in the equation of the plane, because that point is on the plane. Okay. And then let's see over, oh gosh, color choices. I'll use green. This point, its height is this z-coordinate there, because this point is on that paraboloid. And so altogether then, the height is just going to be, well, that z-coordinate minus this z-coordinate to give you the height. And then for each one of these little French fries, there's going to be a corresponding area down here in the shadow, and that is dA. So now I still haven't talked about the domain, but I am just making the observation that the total volume is the sum of these individual volumes. These individual volumes are height times the area of the base. Is that cool so far? Okay. All right, so what's the domain? Right? It didn't tell us a domain. We're going to have to figure out for ourselves what the domain is. And I hope it's pretty clear that the domain is this shadow down here. It's kind of it's that shadow down in the XY plane. But what is that? What are those points? Okay. Let's think in terms of finding this boundary curve for the domain. That boundary curve comes from this kind of edge, if you will. That edge, geometric appeal, is the intersection of this plane with this paraboloid. And here's where a lot of students mess up. Surprising number of students will do the following. And that is, they'll say, oh, okay, well, I'm interested in these points that are where these two surfaces intersect. These two surfaces have these two equations. I'll set the equations equal to each other. I don't know who came up with this. There must be some high schools out there that are pushing this. It doesn't make any sense. Setting equations equal to each other is just not, it's almost meaningless. For example, what a lot of students will do is they'll say, all right, I guess I need this to equal to this then. They speculate. Well, this equation, I happen to write it like I did here, but I could have subtracted this 7 over to the other side and have a 0 on the right-hand side, in which case I'd be setting x squared plus y squared equal to blah, 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 minus 7. Why wouldn't I do that? Which way do you do it? Right? It's not clear what actually does it mean to say one side of an equation. This just doesn't make any sense. Is everybody all right with that? Okay. So let's talk about how to make a proper interpretation of this, and what is it that I can really say about these points that I'm interested in. Like, well, I wanted to be in the highlighter, in the pen mode. Points like this, or more to the point, points like this corresponding to points that are on the intersection of these two surfaces are points where if I look at how high I have to go to get to the green surface, and if I look at how high I have to go up to get to the blue surface, same height. Right? After all, the points that we're interested in here, these are points where Z1 is equal to Z2. So that's what you set equal to each other. I need to set this equal to that. What do you think? Yeah.
You just need to see that.
Okay, so the point to the defining characteristic of these points that we're interested in is that where the green intersects the blue. That means for given xy, I need the green altitude to be the same as the blue altitude. And the altitudes are z's, and so I need those z's equal to each other, right? So all you got to do then is, let's see, I'll do it like this. So set these two z's equal to each other. In other words, now you're going to have to do a little bit of algebra solve for these two different z's. One of them's already solved for. How convenient, right? But setting those two z's equals to each other gives you this, and then a little bit of algebra gives you this. That's the equation of that circle. And once you know the equation of this circle, then you can slice it up in the usual way. dy dx, dx dy, take your pick. Doesn't make much difference in this case. And a bunch of details that follow that aren't the point of this example. Yeah.
Is there ever a case where the domains not in the xy, so you have to set them equal?
Oh yeah, sure. I mean, it might be in the YZ plane or the XZ plane, something like that. Yeah.
And so you need to set, like you always set the, you know how you're saying the, like z of x, y, like
Yeah.
If it was like in the YZ plane, would it be the x equal?
The devil's in the details, so I'm not going to answer that question because I don't want to say always to an ambiguously stated thing. I mean, I know where you're coming from, right? Probably, but details make all the difference. So you always have to do what makes sense in the situation, and this is just one example of how to treat a particular situation. Yeah.
So what does the domain end up being?
Yeah. So this curve that I have in purple there, that curve has that equation. So the domain is just what's inside of that curve. The domain is this shadow that I have in orange now.
Yes, but like if we were actually going to write the bounds of that equation, what would?
Oh yeah, you got to go through one of these slicing processes, right? And again, not the point of this example. You're going to have to decide you want to do dx dy or dy dx, and so you'll be slicing up this circle instead of slicing up a triangle or whatever. But you just follow the same process. Totally works. Yeah. Right. Okay. Last little comment on this, and then we'll go on to the next section, and that is you'll notice in this algebra that I had to complete the square. There and there. Do y'all remember completing the square? Did y'all get told the same nonsense that I did when I was in, I don't know, early high school or whenever that happens? That you don't really need to do completing the square. That's just for when you're solving a quadratic equation. We already have the solution formula for the quadratic equation, so you don't really need to know that. Nonsense. Right? Completing the square is a very handy algebraic method. Note here, we are not trying to solve a quadratic equation, and completing the square is still useful. So this is underappreciated algebra. I think everyone needs to know how to do it. It is commonly blown off in high school, so if you may be one of those students who either never saw this or maybe you saw it but they didn't emphasize it or for whatever reason you don't remember it or whatever it is, it's a good thing to make sure that you know. There's internet resources if you like that sort of thing. You're also welcome to come to my office hours, and I'll be happy to show you how it works. Okay. All right. Okay, this next section is super quick. This will take us about 5 minutes, I think. This book has some weird features. Section 5.3 is about a 5-minute conversation. Section, which one is it? There's a couple of sections, I don't remember what the numbers are, that are 3 or 4 full lectures. And so it's very kind of random about how big the different sections are. Okay, so the idea here, changing the order of integration. Recall when we talked about rectangular domains. You remember I did this move right here, right? You can switch the differentials just so long as you switch the bounds correspondingly. But then I said only for rectangles. Okay, so here we're going to address what happens when it's not a rectangle. Roughly speaking, it's a pretty straightforward process. If you have an iterated integral, let's see here, I can zoom out a little bit more. Cooperate? Yeah, if you have an iterated integral, just reverse engineer the double integral that gave rise to it. I'll show you the details in just a second. But we're going to undo that, find the original double integral, and then that double integral we're going to just turn into an iterated integral by slicing the other way. So not a particularly sophisticated process. Let me show you how the undoing works. How do we reverse engineer the domain? And so here we go. It says right here that y goes from 0 to 1, so there you go. Y equals 0, y equals 1. We know our domain's got to be between those two lines. We also know that for a particular value of y, my lower bound for x is y so draw that, x equals y. And I also know that for a particular value of y, my upper bound for x is x equals 1. So let's see here. So here, let me put all this on the same diagram. So we're going to start at y equals 0. We're going to end at y equals 1. And for any value of y in between, we're going to go from the light blue to the dark blue. And with all of that given, now what are the points that we sweep out in going from between the two green lines from the light blue to the dark blue, and we get this triangle that I have shaded here. That's our domain. That's all there is to it. Okay, and then you can slice that up in the other order. This is all the usual. I'll let y'all think it through as to why when you slice in the other order, it turns the integral into this. Okay, notice the bounds are not this thing, right? They're not just switching the bounds, right? We had previously, let's see here, the x bounds had been from y to 1. Well, these x bounds are not y to 1. Totally different. Everybody see that? Again, only for rectangles do you get that kind of convenience. Okay, why would we ever do such a thing? What's the purpose of this? We had seemingly a perfectly good iterated integral. Why didn't I just plug and chug with this? And well, sometimes you get unlucky, and if you look at this inside integral, your integrand is e to the x squared. You need to take an antiderivative then of e to the x squared with respect to x, and you can't do it without like power series and stuff. We don't want to. Yeah. So this seemingly innocent-looking iterated integral is actually a just non-starter. We just can't even start. It's dead in the water. So what do you do when you are stuck? Well, you try something, right? You fingers crossed. I'm going to I don't know, maybe do a substitution or something. You turn the question into a different question and hope that the new question might be easier. So when we switch the order and get the all new bounds, etc., now we look at this thing. Let's look at the inside integral. The inside integral, I still have e to the x squared, but now keep in mind y is the integral. Excuse me, y is the variable. The outside variable is a constant. The outside variable is x, is a constant. That means that's a constant. That means all of that is a constant. We're just looking at an integral of a constant between 0 and x. And so we get this as our new integrand. Now, it remains that we've still got this scary looking expression here looking at us in an x integral, and so this at a quick glance does still look scary. But now we have this extra factor of x right there, and that makes this substitution make that integral work out just fine, and this is totally doable. Pretty straightforward. Everybody good? So it doesn't happen super often that you find yourself with a dead-end iterated integral that turns super convenient when you do the switcheroo, but every so often. So it's a good little method to be aware of. Okay, so let's talk about triple integrals a little bit. Just to kind of get the ball rolling, let me just remind y'all what we did with double integrals. The whole point of double integrals is to recognize that sometimes you need to take some accumulating quantity, where the whole is the sum of the parts, then break it up into parts, deal with each part separately, and then add them up. In other words, Riemann sums. Right? So all we did to define double integrals is just make sense out of what do you mean by chopping up a two-dimensional domain and then dealing with some simple question on that each little piece of that two-dimensional domain. And a bunch of details follow. So, same in 3 dimensions. What if I have mass? It's not mass distributed across an interval. It's not mass distributed across an area. What if the mass is distributed across a volume in space? Okay, well, yeah. I mean, break it up into little pieces. Right? These little pieces, little formal details. When you slice in the various different directions, you will, among other things, be slicing up the z-axis. And so, yes, you do have to write down corresponding new formulas for delta z and z sub k, et cetera, et cetera. That's just kind of details that have to get written down. Right? But it remains that you can take a whole problem where the question might be hard. You can break it down to a bunch of little pieces. Each little piece, let's say I wanted to know how much mass is in this piece. How much mass is in this little tiny little piece of volume, this little teeny little volume? Well, mass would be mass per unit volume times volume. Right? Just like with double integrals, we were talking about mass per unit area times area. Just like in single variable integrals, we were talking about mass per unit length times length. It's same idea, just now sort of 3-dimensional. And so on each little piece, oh, that's the wrong color. On each little piece, whatever our accumulating quantity is, I don't know, let's just say mass, whatever. Your integrand is quantity per unit volume. This then says multiply by volume. That gives you quantity in each little piece, and then you add up over all the pieces. So this strategy, this Riemann sum strategy, the chop it up, add it up strategy, this is what it looks like when you're on a 3-dimensional domain. And then I think the notation's pretty believable, that it would make sense to refer to this with that notation. Again, we have little pieces of volume represented by delta x, delta y, delta z. And last comment, and then we'll call it a break. This right here That is a single symbol. This is not a single variable integral of a single variable integral of a single variable integral. That is not what this is. Right? This is a brand new symbol that I created by taking three separate integral symbols and kind of shoving them together, right? It represents this thing. Okay, we'll pick up here next time. Y'all have a great break. See you later. All right. Don't forget about attendance.